According to the National Electrical Code, the conductor size for the 120 volts alternating current circuit should be based on the maximum overcurrent protection device in the system. In this case, the 60 amps fuse is the maximum overcurrent protection device, so the conductor should be sized for 60 amps. The reasoning behind this is that the conductors must be able to withstand the maximum amount of current that could flow through them under fault conditions. If the conductors are undersized, they could overheat and potentially cause a fire. The fact that the remote panels have their own main circuit breakers is irrelevant. The conductors still need to be sized for the maximum overcurrent protection device in the system, which is the 60 amps fuse. To further clarify this, let's examine some relevant sections of the National Electrical Code. NEC Section 310.15b16 states that conductors shall be sized to carry the maximum possible current without overheating under normal conditions. This means that the conductors must be able to safely handle the 60 amps that the fuse is rated for. NEC Section 310.15 further reinforces this point by stating that conductors used for branch circuit shall have an ampacity not less than the rating of the branch circuit overcurrent device. In this case, the branch circuit overcurrent device is the 60 amps fuse, so the conductors must have an ampacity of at least 60 amps. Now let's delve a bit deeper into understanding ampacity and its significance in conductor sizing. Ampacity refers to the current carrying capacity of a conductor, expressed in amps. It's the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. Factors that influence ampacity include the conductor material, size, insulation type, and ambient temperature. When selecting conductors, it's crucial to consult ampacity tables provided in the National Electrical Code, such as Table 310.15b16, to determine the appropriate conductor size for a given current rating and operating conditions. These tables provide ampacity values for various conductor types and sizes, considering factors like insulation temperature rating and installation methods. For instance, a copper conductor with THHN insulation might have a higher ampacity than the same size conductor with a lower temperature rated insulation like TW. Furthermore, the National Electrical Code outlines certain factors that must be applied to ampacity values under certain conditions. Dating is necessary when conductors are installed in close proximity to each other, exposed to high ambient temperatures, or run through conduits with multiple conductors. These factors can increase the conductor temperature and reduce its current carrying capacity. For example, if multiple conductors are bundled together in a conduit, the ampacity of each conductor must be reduced to prevent overheating. Similarly, if conductors are installed in an area with a high ambient temperature, the ampacity must be derated to account for the increased heat. To ensure compliance with the National Electrical Code and safe operation of electrical systems, it's essential to carefully consider all applicable derating factors when selecting conductor sizes. In the context of your PLC control panel and remote panels, the 60 amps fuse serves as the primary overcurrent protection device for the entire circuit. This means that the conductors must be sized to handle the full 60 amps, even if the individual circuit breakers in the remote panels are rated for low currents. The reason for this is that a fault condition, such as a short circuit, could potentially draw the full 60 amps through the conductors before the remote panel circuit breakers have a chance to trip. If the conductors are undersized, they could overheat and cause a fire before the overcurrent protection device can react. It's also important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, you may need to increase the conductor size, especially for long circuit runs. Several factors contribute to voltage drop in electrical circuits. Firstly, the length of the conductor plays a significant role. Longer conductors offer greater resistance to current flow, leading to a more substantial voltage drop. Secondly, the conductor's cross-sectional area affects voltage drop. Thicker conductors have lower resistance and therefore experience less voltage drop compared to thinner conductors. Thirdly, the amount of current flowing through the conductor influences voltage drop. Higher current levels result in a greater voltage drop due to increased resistive losses. Lastly, the conductor's material affects voltage drop. Copper conductors generally exhibit lower voltage drop than aluminum conductors for the same size and current due to copper's lower resistivity. To mitigate voltage drop issues, engineers often employ various techniques. One common approach is to increase the conductor size, which reduces the resistance and voltage drop. Another strategy involves shortening the conductor length whenever possible to minimize resistive losses. Additionally, using conductors with lower resistivity, such as copper, can help reduce voltage drop compared to using aluminum conductors. Proper circuit design and load balancing are also crucial for minimizing voltage drop, ensuring that each circuit is adequately sized to handle its intended load. Furthermore, regularly inspecting and maintaining electrical connections can help prevent loose connections, which can contribute to increased resistance and voltage drop. By carefully considering these factors and implementing appropriate measures, engineers can effectively manage voltage drop and ensure the reliable and efficient operation of electrical systems. Let's consider a practical example to illustrate the importance of proper conductor sizing. Suppose you have a 120 volts alternating current circuit that feeds a motor in one of the remote panels. The motor has a full load current rating of 20 amps, and the remote panel circuit breaker is rated for 25 amps. However, the conductors feeding the remote panel must still be sized for the 60 amps fuse in the main PLC control panel. If you were to undersize the conductors to, say, 30 amps, they could overheat and fail if a fault condition caused a current draw exceeding their ampacity. Therefore, it's essential to follow the National Electrical Code guidelines and size the conductors for the maximum overcurrent protection device in the system, which is the 60 amps fuse. In addition to conductor sizing, it's also important to consider the type of conductors used. The National Electrical Code specifies different types of conductors for various applications based on factors like insulation type, temperature rating, and resistance to moisture and chemicals. For example, THHN conductors are commonly used in dry locations, while THWN conductors are suitable for wet locations. When selecting conductors, it's important to choose a type that is appropriate for the environment in which it will be installed. The National Electrical Code provides detailed information on conductor types and their applications in Chapter 3, Wiring Methods and Materials. This chapter covers a wide range of topics related to wiring, including conductor identification, installation requirements, and installation method. It's essential to consult this chapter to ensure that you are using the correct type of conductors for your specific application. Furthermore, proper installation techniques are crucial for ensuring the safe and reliable operation of electrical systems. The National Electrical Code provides detailed guidelines on installation methods for various types of wiring, including conduit, cable trays, and direct burial. These guidelines cover topics such as conductor spacing, support requirements, and protection against physical damage. When installing conductors, it's important to follow these guidelines carefully to prevent damage to the conductors and ensure that they are properly protected. Improper installation can lead to a variety of problems, including overheating, short circuits, and ground faults. These problems can pose a serious safety hazard and can also damage equipment. Therefore, it's essential to ensure that all electrical work is performed by qualified personnel who are familiar with the National Electrical Code and proper installation techniques. Now let's discuss grounding and bonding, which are critical for electrical safety. Grounding is the process of connecting electrical equipment and systems to the earth, providing a low impedance path for fault currents to flow back to the source. Bonding is the process of connecting metallic parts of electrical equipment together to create an electrically conductive path. The purpose of grounding and bonding is to minimize the risk of electric shock and to provide a path for fault currents to trip over current protection devices, such as circuit breakers and fuses. The National Electrical Code provides detailed requirements for grounding and bonding in Article 250, Grounding and Bonding. This article covers topics such as grounding electrode systems, equipment grounding conductors, and bonding jumpers. It's essential to follow these requirements carefully to ensure that electrical systems are properly grounded and bonded. Improper grounding and bonding can create a dangerous situation, as fault currents may not be able to flow back to the source, potentially energizing metallic parts of equipment and increasing the risk of electric shock. Therefore, it's crucial to ensure that all electrical work is performed by qualified personnel who are familiar with the National Electrical Code requirements for grounding and bonding. In summary, when sizing conductors for your 120 volts alternating current circuit in the PLC control panel with remote panels, it is crucial to adhere to the National Electrical Code guidelines. The conductor size must be based on the maximum overcurrent protection device in the system, which in your case is the 60 amps fuse. Even though the remote panels have their own circuit breakers, this does not change the requirement for sizing the conductors based on the 60 amps fuse. It's also important to consider factors such as ampacity, voltage drop, conductor type, and installation methods to ensure the safe and reliable operation of your electrical system.